Good evening all. Let's get started with this week's session. So the first problem is you have a steam power plant with this is the turbine inlet, condenser inlet, pump inlet, boiler inlet and the boiler outlet. So you see something like this. So the inlet to the turbine is at 60 bar 380 Celsius, and then it goes into the outlet is at that particular value 0.1 bar to 9.9. So this is in the superheated state, and then you are going inside the dome, and this goes inside the condenser. Now from the condenser it again goes into the pump. So this inlet is the saturated liquid. The saturated liquid goes into the pump, and from the pump again you heat into it goes up. The pump goes from 0.09 bar to 70 bar, and then it goes into the boiler where heat is added and pressure temperature both are increased. Now you can see that the pressure here and here are different. This is because of the connection piping between the boiler and the turbine. Because of this there is a pressure drop, and there are some heat losses. Because of this the temperature also reduced from 400 Celsius to 380 Celsius. Now this is clear. With this, what are we required to find? We are required to find the power output of the turbine. So if I know state 1 and state 2, H1 minus H2 should give the power output. Heat transfer in the boiler and the condenser separately, and mass of cooling water circulated per hour in the condenser. How do we calculate it? Power output is straightforward. H1, you know the state 60 bar 380 Celsius, so you can directly report to the steam table to get the value of H1. And HF2, you know 0.1 bar and 0.9 dryness fraction. So HF2 is this, Hg, you can calculate HFG from their X2. So H is basically HF plus X times Hg, so that will give you the value of H2. Once you know H1 and H2, and assume a mass flow rate of 1000 kg per hour, and that should directly give you the power of your turbine. Similarly, you can also calculate in the boiler. So I know, so for the boiler, my input is at state 4, my output is 65 bar 400 degrees Celsius. Let's call this as state A. So HA can be calculated, HF4 can be calculated. So Q is mass times input output minus input, so HA minus HF4. So this is also straightforward. Similarly, inside the condenser, so this is my condenser. So the inlet is 0.1 bar 0.9 dryness fraction. So you can calculate H2. Similarly, this is saturated liquid 0.09 bar. So you can calculate H here also. Once you have both the H, you can directly substitute to get the value of condenser. So now determine the water flow rate in the condenser. So the condenser is actually rejecting heat to something. So that heat rejection is something that we have to, the amount of mass flow rate of water. So here it is given that the condenser is rejecting heat from the water, and this water is from getting heated from 20 to 30 Celsius. So whatever is the heat absorbed by the water should be equal to the heat rejected by the condenser. So that is the energy balance that we are doing here. So QC should be equal to QW, where QW is mCp delta T. You have the Cp, and then once you substitute, you will be able to get the value of mass flow rate. The last question asks you to find the diameter of the pipe. So how do I calculate that? I equate the mass flow rates. So if you see from the turbine outlet to the condenser, so here you have a dryness fraction of 0.9, which means most of it is in the vapor phase. So your dominant the pipe diameter will majorly depend on your vapor fraction. The fraction of your most of the fraction of your pipe will be because of your steam instead of your liquid one, and liquid also have a very high density, so it doesn't actually occupy much of the volume. So just to incorporate that effect, I multiply the dryness fraction with the Vg value. So this should give me the actual volume fraction inside. Yeah, of course you can directly use instead of using this X times Vg, you can directly put Vf plus X times Vfg, which is also okay. But then like since it is X value is 0.9, Vf will be very much less compared to Vg. So this is an approximation, it will be equal to that, just to simplify the calculation. Once you substitute this, you will get the value of V directly. Now the second problem is also very similar. The only difference is you are required to find the efficiencies. So what is given here is you have the supply. So whenever you say the steam supply is at 15 bar, what are you supplying this to? Yeah, you are supplying this to the turbine. So the turbine inlet is 15 bar and dry and saturated. So you're in the saturated state. The condenser pressure is 0.4 bar. Calculate the Carnot and Rankine equation. This is again straightforward. So you know P1 and P2. So first state is dryness fraction, the pressure. So you can directly calculate the temperature and enthalpies. Similarly, for the second state, I don't know the dryness fraction. So without dryness fraction, I will not be able to calculate enthalpies. So in order to calculate enthalpy, I need to now assume that there is an isentropic process from the turbine inlet to the outlet. So basically, it's an isentropic expansion. So S here is this one. So you equate that with the S2 that you need to find. So S1 equal to S2, from which you can substitute that and get the value of X2. Once I have X2, I can calculate my enthalpy. Now, how is the efficiency defined? Efficiency for Carnot cycle is direct. That is 1 minus sink temperature by source temperature. Your sink is your condenser, source is your boiler. So you substitute those temperatures to get the value of Carnot efficiency directly. This is very straightforward. Now, Rankine efficiency is also very similar. So the efficiency is defined as your output divided by your input. So the output is your turbine work that you are doing, and your input is basically the heat that you are supplying to your boiler. So if the isentropic expansion is from state 1 to state 2, this is the amount of work that you are doing, H1 minus H2. Of course, there will be some amount of work done on the pump that you have to minus here. I'm neglecting that. We will see in the coming problems that the order of magnitude is very different, that you can actually neglect that. It will be less than 1% error. So I've already taken that. Just bear with me for a couple of minutes. We will see in the next problem what these orders are. Divided by your heat supplied is H1 minus HF2. So you have H1, HF2, all these values. So you can directly substitute them to get the value of Rankine efficiency. Are there any questions in this? Okay, if there are no questions, we'll move on to the next problem. So here we have a steam turbine that is supplying steam at 20 bar, 360 Celsius. Sorry, this is the inlet of the turbine, and then it's expanded to 0.08 bar. We don't know what is the final quality. It then enters a condenser where it is condensed to a saturated liquid water. The pump feeds back the water into the boiler. Assume ideal processes, so the expansion is isentropic, the compression is also isentropic. Find per kilogram of steam the network and the cycle efficiency. Okay, so if you put it on a TS plot, this is how it looks. From state 1 is superheated, and then it goes isentropic expansion. This is a condenser heat rejection, and then you have anisotropic compression here. And from there again you have constant pressure heat addition. So this is straightforward. So P1 is 20 bar, P2 is 0.08 bar. At 20 bar and 360 Celsius, you can calculate from the superheated steam tables enthalpy and entropy. Now I need to calculate the enthalpy at state 2. So for that I need to know the dryness fraction here. So what I will do is I will assume an isotropic expansion, since it is given that assume ideal processes from 1 to 2. So S1 equal to S2. S2 is basically SF plus X times SG minus SF. So that is this. So from there you get the value of X2. Once I have X2, I can calculate H2 as HF2 plus X times HFG. So once I have H1 and H2, I can directly calculate the work done. So now for the turbine, this is straightforward. Now for the pump, how do I do that? For the pump, work is essentially DH, is du plus PdV plus VdP. So what happens in the pump is it is in the saturated liquid state. So the density of liquid is very high. Water is around 1000. So the specific volume will be around 10 to the 10 raised to the minus 3. So delta V at 10 raised to the minus 3 is very less, that this term will actually be neglected. And the temperature rise will also be very small, so you can practically neglect du also. So both of these terms can be neglected, and work done is approximately equal to V times delta P. So V is your specific volume at this state 3, that is equal to Vf2 times the delta P is P1 minus P2, the difference in the pressure between the boiler and the condenser. So that should give you the value of Vf2. So those are the things that are asked in the question. And okay, you're also asked to find the network and cycle efficiency. So how do I calculate the efficiency? So I have network done as work turbine minus work done by the pump. Turbine work is 2187.68 minus 2.151. See again, just as I mentioned, you can see the work done from the turbine is, sorry, is 971.62. So you can see the difference between this and this. So it's compared to 971, 2 is very less. So we usually neglect the work done on the pump part. Okay, now to determine the efficiency, I need to calculate the heat supply. So what is the heat supply to the boiler? The heat supply to the boiler is H1 minus H4. So how do I calculate H4? So just as we said, work done is basically DH. So the work done by the pump will be H4 minus H3, and H3 is basically HF2. So from this relation, we can calculate H4 is HF2 plus the work done by the pump. So HF2 is something we already know from here, 173.88 plus work done by the pump is 2.151. Now I have H4, I can substitute in the previous equation, use H1 minus H4. H1 is 3159.3 minus H4 is 176.031. Now I have Q as well as the net work done. So the efficiency can be calculated as net work done by your heat supply. So the net work done is 969.469 divided by the net heat input is 2983.69. That is around 0.324, around 32.4% efficient. Okay. Are there any questions in this? Okay. If there are no questions, then we move on to the next problem. So again, here you have a Rankine cycle operating between 80 bar and 0.1 bar. The maximum cycle temperature is 600 degrees Celsius. So this will be, where will this be? Where will the maximum temperature occur? It will occur either at the turbine inlet or at the boiler outlet. So if there are no heat losses in the pipe connecting the boiler and the turbine, both of them will be equal. Otherwise, it will be at the boiler outlet temperature. If the steam turbine and the condensate pump efficiencies are 0.9 and 0.8 respectively, calculate the specific work and the thermal efficiency. You don't have to look up the steam tables, the values are directly given here. If you plot this, so this is what it looks like on a TS plot. So from 1 to 2 you have isentropic and then constant pressure, isentropic and constant pressure. So again, it's the same process that we have followed. Whenever you are required to find the turbine work, this is an isentropic process. So first you calculate H1 and S1 and then equate S1 equal to S2, and this pressure will be given to you. So you can take SF, SG and calculate the quality from there. Once you have the quality, calculate the enthalpy from the quality. So that's what you will be doing always. So S1 equal to S2. From there you calculate the quality. Once you get the quality, substitute that to get the value of enthalpy. Once you have the enthalpy, calculating work is easy. That is H1 minus H2. This is the work done in case of an isentropic process. But now it is given that the efficiency is 0.9%, which means the actual work output from the turbine will be less than the theoretical one that you have calculated. So this will be 0.9 times whatever you have calculated in an isentropic process. So this is clear. Similarly, for the pump, we have derived the formula just now. So it will be V times delta P. V is the specific volume at this state at the inlet of your pump. So from there, you can directly calculate work. Again, in case of a turbine, the work output will be less than in an isentropic case. In case of a pump, you are giving the work. So it will be more than whatever is in the ideal case. So we have to divide it with this efficiency to get the work done from your pump. Now efficiency is again, you calculate the net work done, that is turbine minus compressor. Here also you can see that this is in the order of 1200 and this is in 10. So this is practically negligible. Again, now you calculate the HQ. So Q is again H1 minus H4. And in order to calculate H4, I can make it approximately equal to HF4. And HF4 I can get from the work done for the pump. It's the same as we have just done now. Right? Are there any questions in this? Okay, if there are no questions, we move on to the next problem. So next one is also a very standard problem. The only difference is up until now we have been discussing problems where your state 1 is in the superheated state, but now we'll have a case where the turbine inlet is in saturated state. The process would be still the same, there won't be any difference there. So again, you will do the same process. So the first one is at 35 bar pressure. So all you have to do is just take some values from the table. So this will be equal to Hg at state 1 because it is in saturated vapor state. So this will be 2802. And similarly, S1 will also be equal to ST1, will be 6.12 H. Once you have S1 and H1, S2 is also at 0.26 bar. I'll have all the values. So HF is 51.5, Hg is 2358.4. Similarly, you can have SF and Sg, or I can directly take SFG, so we can calculate X directly from it. SFG is and I would also require to calculate the pump work, so I would require the PF here. Okay, now I've written all the values, so we just do the calculation now. First, let's calculate the easiest part, pump work. So we have just defined that pump work is basically your PF, I'll just call it 2 times delta P is P1 minus P2. So this is very straightforward. You have all the values, so you have to just substitute 35 minus 0.2 and then just to convert into units. So here it is taken that assume mass flow rate of 9.5 kg per second. So I'll just multiply that here. That's around 33 kilowatts. So are there any questions in this part? I don't think there will be any questions. So the next one is the turbine work. Again, this is also straightforward. All we need to know is calculate the value of H enthalpy at state 2, for which we need to know the quality. So again, we will follow the same process. So we'll start with S1 equal to S2. And from there, S1 we already know as 6.1228 equal to S2 is SF2 plus X2 times SFG2. So you can equate that. So SF is 0.8321 plus X2 times SFG is 7.0773. This should be equal to S1 6.1228. So if you solve this, you get X2 equal to 0.747. Once I have X2, I can directly calculate H2. H2 is HF2 plus X2 times Hg2 minus HF2. I have used the wrong one. So you can directly put this as HFG2. So you can directly substitute the values. HF2 is 1.5, X2 is 0.747 times HFG2 is 2358.2. Now I have H1 and H2, so I can calculate the work done by the turbine as your m dot times H1 minus H2. M dot is given as 9.5 times H1 minus H2, H1 2H02 minus 2013. That's it. That's your turbine work. Now, what is the third part is to calculate the Rankine efficiency. So, how do you calculate the Rankine efficiency? Which we have done just now. So, I'll directly write. So, it's basically whatever is the work done divided by whatever is the heat supplied. So, heat supplied is H1 minus approximating it with, you're essentially neglecting the pump work. So, you have all the values with you. So, I'll directly substitute the values here. So, H1 is H1 we have 2802 minus H2 is 2013 divided by H1 minus HF2 is 21.5. That is around 0.309. This is also straightforward. The next one is to determine the condenser heat flow. So condenser heat flow is H2 minus H3. N times 2 minus H3. M is 9.5. H2 we have already calculated 2013. H3 is HF2, that is 251.5. 16,734.25 kilowatts. And the last part asks you to find the dryness fraction. Dryness at turbine exit. This we have already calculated, so that is basically your x2, which we have already got as 0.747. Are there any questions in this? Yeah, I hope there are no questions in this. So next we have a little bit of a problem. We have a steam turbine that is fed with a steam. So up until now we have been discussing the normal traditional Rankine cycle. This is a Rankine cycle where you have an extra loop in between. So what is happening here is steam turbine is fed with the steam. So this one having an enthalpy of 3100 kilojoule per kg, it moves out of the turbine with an enthalpy of this is out of the turbine at an enthalpy, both of the states have the same enthalpy of 2100 kilojoule per kg. Feed heating is done at a pressure of 3.2 bar. So feed heating is done at a pressure of 3.2 bar. So this is the feed heater that is shown here. And with the steam enthalpy, the steam at enthalpy of 2500 kilojoule per kg. So a part of this is coming and then that is used as feed heater. So this is your regenerative cycle. And then the condensate from the condenser. So this is the condensate from the condenser, state 4, with an enthalpy of 125 kilojoule per kg enters into the feed heater. So this as well as this, both of them enter here. The quantity of the bled steam is 11,200 kilogram per hour. Find the power developed by the turbine. Assume that the water leaving the feed heater is this, that is going into your pump, is saturated liquid at 3.2 bar, and this is what that will go into the pump and it will reach state 6, and the heater is a direct mixing type. So what do you mean by direct mixing type is basically both of this gets mixed and eventually it comes, so you can apply your energy balance. That's what we are saying. So how do I solve this problem? So what am I required to find is what is the net power output of the turbine. So what are the knowns here and what are the unknown quantities here? So let's write the equations one by one. So net work by the turbine is what? W equals to whatever is your input minus, there are two outputs here. H2 is this one, but only m kg of it is actually coming in state 2 and 1 minus m is going in state 3. So inlet minus outlet. So this will be m times H2, and then you have 1 minus m going into state 3. So that will be 1 minus m times H3. So this is the net work done by the turbine. So that is H1 minus mH2 minus 1 minus mH3. So what are the values that are given in the problem? Do I know H1? So the steam turbine is fed with a steam having an enthalpy of 3100. So it is already given to me that H1 is 3100. And then do you know the value of H2? So it says that the feed heating is done at a pressure of 3.2 bar with the steam enthalpy of 2500 kilojoule per kg. So the feed heating is done by the outlet of this stage. So this state is equal to this state, and that is state 2. The state 2, it is given enthalpy is given as 2500 kilojoule per kg. So state 2 enthalpy is already known. So what else do I need to know? Do I know the value of state 3? Do I know H3 value? So again comes the next part. So it says that the condensate from the, it moves out of the turbine with an enthalpy of 2100 kJ per kg. So what is coming out of the turbine is state 3. So this is the outlet of your turbine. So state 3 is also given to me. So H3 is given as 2100 kJ per kg. So in order to calculate the work done, my only unknown is the fraction of mass that is actually diverted to your feed heater. So how do you calculate this fraction? So how do I do that? Is again I need one more equation to do that. That is where the energy balance of the feed heater comes. So the feed heater has two inputs and one output. So if I apply the energy balance for the feed heater, what do you have is let's say for the unit mass of your whatever output that you have. So the net thing, the net change is as 1 minus m is coming from this, and 1 minus m is coming at an enthalpy of state 5, and it is said that the outlet of the pump is the condensate from the condenser with enthalpy of this enters into the feed heater. So this is in the saturated liquid state. So I will use the relation 1 minus h times 1 minus m times hf5. This is one input. The other input is coming from state 2. So that is mass m times 2 should be equal to your outlet. So the outlet will be 1 minus m plus m. That is 1 times the state here. What is the state here? So it says that I assume that the water leaving the feed heater is saturated liquid at 3.2 bar, and it also says that the feed heating is done at a pressure of 3.2 bar with steam at enthalpy of 2500 kilojoule per kg, which means that this state 2 is the same state that is maintained here. So what is happening to the steam is the steam that is coming here is getting converted into the saturated liquid at the same pressure. So I'm calling this as 1 times HF2. How do I calculate HF2 now? So basically we know the pressure. So at 3.2 bar, we can directly get the HF2 value. Just look up the steam tables, that's the value we're getting. And once I have HF2, do I know the value of HF5? So HF5 is the output of your condenser. So it says that the condensate from the condenser is an enthalpy of so and so. So H5 is also given to me as 125. So I have HF5, I have HF2, I have H2 already. So I can solve this equation to get M. So if you solve for m, so that comes as 0.226. So now what is this m? This m is a fraction of heat that is getting diverted. So out of 1 kg that is input, around 0.226 is coming into this one, and the remaining is actually coming as output. So from this you can directly calculate. Should have put something here. So the net work output will be m dot. So how do I calculate this m dot? This m dot is the mass flow rate in the total system. So how do I calculate m dot? So that is again straightforward. It's given in the problem directly here. The quantity of the blood stream is 11,200. So that is already given to you. So m dot is 11,200 is the total quantity of steam. So how much of this is actually supplied to the turbine? So blood stream is this one. So divided by your total mass fraction. Okay. Let's take only up to one decimal. So this is m dot. Now I have m dot, I have all the enthalpies, I have the mass fraction. So I can substitute them to calculate the work done. So work done is m dot. I'll just convert this into kilogram per second. So that will be 49557.5 divided by 3600 times H1 is 3100 minus mass fraction times H2 is 2500 minus 1 minus mass fraction times H3 is 2100. Okay. Are there any questions in this? Okay, I guess there are no questions. So we have around 10 minutes left in this session. So this one is a bit of involved problem, so I don't want to start it now. So we'll have an extra session next week on probably next Saturday. You'll on so this is 12, so we'll have next session on 19th of this month, next Saturday. So you will receive a mail from the NPTEL team regarding that, and we'll discuss the last couple of problems that we are left with now. So basically, the other ones will a couple of problems on the refrigeration cycle, vapor compression cycle, and then I have one more problem on the Brayton cycle that involves regeneration as well. So with this, we'll be able to cover all entire syllabus up until week 12. So this involves a little bit of discussion. So we'll we'll keep this in the next week. Do you have any questions? Yeah, if there are no questions, then we'll meet next week. Thank you for joining.